Okay, one of them that I just have to hit, I have to hit, is calibration. Okay, so let's talk about calibration. Let's talk about calibration and any logic, and let's see how brutally short I can make our coverage of calibration and still hope to give some glimmer of meaningful understanding from it. Sure. Sure. Wow. That's great. So much of the motivation, as I frame it, for calibration lies in the fact that we often have data gradients which we experience in our model. We have lots of data about some things and few data about others. And sometimes, in particular, we have a paucity, a shortage of data about certain parameters to inform those particular parameters, but we may have quite a bit of data about overall system behavior that in some sense constrains our guesses as to what those parameters might be. Quite a bit of data on how the system as a whole behaves, and that data typically can't be used to inform an estimate of any one given parameter, but it constrains our understanding about what possible values of parameters may be in combination, because we want the behavior of the model to be in some sense consistent with or consonant with the behavior of that's observed empirically. And I think many of you know, in contrast to sort of a classic statistical model where we have one dependent variable and several independent variables, here we're often dealing with a situation where we have a variety of empirical data we can bring to bear, and where we're seeking a given model to simultaneously match diverse data sources, diverse data points, potentially diverse time series. And in those conditions, in some cases where we have this data that doesn't boil down to any one parameter, we can use backing out methods. We could sort of, through algebraic manipulation and imposing some simple assumptions, we could try to figure out and try to estimate models for parameters. And it boils down to some neat little algebraic word problems. But more commonly, we have to sort of triangulate, as it were, from a bunch of different data sources. And calibration in its classic form is used through much of modeling, involves tuning values of less well-known parameters so that the model output best matches observed data. And here the observed data often corresponds to emergent patterns of behavior from the whole or pieces of our model. And this is one of the key areas where we learn about our model. We get the most insight because quite often in my experience, this is where we find our model just doesn't jibe with the data. We twist and turn and we try to get it into shape and to adjust things, and it just doesn't cut it. It matches some data, not others, and then we change this parameter, it matches the other data but not this data, and we squeeze the balloon one place, it pops out another. And that causes, I've been in that situation many times. It's a little bit frustrating, but it's a little bit enlightening in the sense that our dynamic hypothesis that we created in our head that seems so promising, so full of life, it just doesn't add up when you logically think it through with the data. And in that case, we often have to go back and we have to examine our dynamic hypotheses and examine the data. There's been a number of times in my experience where this has happened, and we've had to make it's given significant insights into model structure because we've explored some things and found that an alternative model structure matches much, much better with the data. And that's a real insight. That's, something you bring home with you as a take-home from the modeling project. Particularly if you could then take that refined model and do some cross-validation with it and find it predicts all this other model data that wasn't used to create it. But other times I've been in situations, this has happened to me several times in my life, where the model, no matter how we attempt, it just will not match the historic data, and we think there's something really, really wrong with the model. And then we talk with the people who are highly knowledgeable about the data, and they said, oh, you don't have to worry about that much. That data is out to lunch. They changed the definition of the data, in this year and changed it back in that year. And so don't, these years in between, don't really take those seriously. And this has happened to us on a number of occasions, and it's breathed a sigh of relief because we took the data as very solid, and it turns out to have actually been problematic for certain regions that we didn't understand. For example, I remember one case we were dealing with kindergartner data, and they told us they changed the definition of kindergarten to include the last year of preschool in a certain year or something like that, and so it threw all our estimates off as to sort of how many kids were in kindergarten. Okay, so calibration really helps us find reasonable specifics for dynamic hypotheses that explain the observed data. It helps us leverage large amounts of often diffuse information we have at our disposal, but can't be used to directly estimate specific parameters. And it helps us undercut or falsify. It's a strong term, but it helps us undercut our confidence in certain models. So calibration, as it's commonly practiced, will use optimization algorithms, often global in character, to adjust unknown parameters so that it matches an arbitrarily large set of data. The data, which is often in the form of time series, informs the objective function of the calibration, and the optimization algorithm will run the model many, many, many times to find the best match. Now, in the context of a stochastic model, the number of runs is especially large because not only do you need to adjust parameter values to find the best match for parameter values, but to really reliably ascertain with robustness what's the best match, you want to run the model many, many times for a given set of parameter values. A given assumption about the parameters, you want to run the models at least several times to develop confidence that the match is not merely a fluke. So, information required for calibration in any logic and other packages include specification of what to match, what are you trying to match up, and then some sort of error function or discrepancy function or penalty function or energy function that specifies how far off we are, or a payoff function or objective function that specifies how good we are, how good a match is. A statement of what parameters to vary, over what range to vary them, and any constraints associated with that, and then characteristics of a desired tuning algorithm. So here we're exploring the sort of space for parameters for different values of three parameters, beta, mu, and tau, and trying to find the point in the space that offers the best match, right? And a given point in this space with a specific value of mu, a specific value of tau, a specific value of beta will often yield different values when run with different random number seeds. So again, you need to take into account those stochastics. Here, I won't go into details and discrepancy metrics, but there's a variety of them that you can use, and we've explored several, including some that take into account the statistical reliability of the data. In fact, that certain data points have a better pedigree than others. We're more confident about them. They were undertaken with a greater number of samples, et cetera. And so we weight them more highly. And there's statistical theories that can be used to back that up. The main thing I want to get to is at a practical level, how do we perform this using the tools that we've been examining? So I'd like you to open up an example model. So go up to Help and look at example models. And I would go to specifically the it's just in the examples. SIR agent-based calibration on the right-hand side. We've opened it before. So Priyasri, you might want to keep your eye out for folks. So who needs TA help? So again, it was under examples on the left, SIR, agent-based calibration. Now we saw this yesterday. We saw it yesterday in parameter variation, and we actually spent some time exploring this little thing. In fact, there are some of my scratchings associated with it, right? Okay, today we're going to explore, we have a different query. Let's go over to the calibration area, all right? Okay, great. So within this context, we have a calibration experiment created by AnyLogic, and here we can specify the characteristics of the calibration according to a number of attributes. We can specify the objective function to use, whether we want to minimize it or maximize it. Here we're using a built-in function, but you could use your own custom function. This function is built-in difference to take the square root of the sum of squares difference between two data sets, and does some interpolation. If I think if maybe the data sets don't have the same number of points, I'd have to double check on that. In any case, it could do with interpolation. I think between data points, and here we specify the number of iterations to run, or whether we want it to automatically stop based on some statistical criteria, the ranges over which the parameters should be varied, and in what sort of levels to explore them if they're discrete, and we are going to explore where some of these sources originated. So here's a bit of autocomplete data on the difference function. So this is again comes in with AnyLogic, and actually I'm looking at the first one, not the second one. There, I should be looking at the second one. Okay. So the difference function is available here. Flex difference between two data sets is square root of the average of the square of differences between linearly interpolated data sets. So this is a built-in function, but you can define your own difference function. For example, this difference function that I defined difference, or that I can't remember. I may have defined it, or someone else did. This difference here, and you could specify your custom kind of difference function for the current result. Okay, this is an example of a custom difference function. Okay, I'd like to explain, however, how this calibration takes place. I've actually a little challenge exercise, or maybe a step-by-step exercise I gave you, that I've been told by my students really help them understand exactly how AnyLogic performs the calibration process. And anyone who's really interested in that, I'd recommend that to them. But if you go to the calibration experiment here, in addition to the attributes we've seen, if you scroll down, you'll see code reminiscent of what we saw yesterday. So this is reminiscent of the code we saw for the parameter variation experiment. And specifically, what we see here is code that indicates what information or what actions to undertake at different points within the experiment run. So here in the initial experimental setup, we're reading in some data from a table function for a data set that gives historic data, and we're putting it into, so we're reading it in from a table function, putting it into a data set. Let's go check where that's done. So here in the calibration, there's this analysis data and table functions. Let's take a look at this table. Oh my gosh, this is something I did in, oh, it's terrible. I did this at UCLA and I screwed it all up. So you folks should see something different, I hope. Is that right? So you, yeah. So I'm clicking in calibration and functions on the left-hand side here under functions. Yeah. Yeah, I think I destroyed it to deliberately see what happens. Okay. That's the table function referred to where we saw that earlier. I'll go to it again. So that's the table function referred to here. So what this is doing is it's reading out of that table function and it's putting it into this DS infectious historic. Okay, it's putting it into a data set. It's taking it out of a table function, putting it into a data set. And then before each experiment run, it clears information on the current objective and the best feasible objective, which are data sets. And after each simulation run, it fills up a certain data set from this root.infectiousDS. Now, who remembers from yesterday to what that refers? Root.infectiousDS. That's main, and it's reading out a what from main? A data set. It's salvaging this data set from main, which was the same data set we saw yesterday. It's the data set recording the number of infectious people over time. And it's saving it to one of our data sets, because main's about to disappear. Main's about to vamoosh. Main's about to be gone, to be destroyed. So we're saving that away so that this is after each simulation run, such that that having saved that away, after each iteration of this, if it's the best iteration thus far, we'll save away the current value of that into what should be best, what's viewed as best. So here, after each realization, it saves this away, and after the iteration for the entire evaluation of a given set of parameters, if that's viewed to be the best one based on the mean discrepancy for that iteration, for that set of parameters, if it's the best one thus far, we'll take the DS infectious current that was saved away for the realization, for one realization associated with it, and we'll save it to the best recorded one. Okay, so that's basically how that works. We have just as in parameter variation experiment, the calibration experiment is running the simulation many times. It's running main many times for different values of parameters, because it's exploring this parameter space, trying to find the best fit to the available data according to that objective function specified above. And in that process, it is actually running the model many, many times. So here, we're reading this DS infectious current out of the main. We have this DS infectious historic that was read from the historic data, and then in the objective function, we're comparing the two. Do you see that? This is comparing DS infectious current, that was the one read from main, with DS infectious historic, which is the one from that table function that I screwed up. And that determines an objective. It determines the goodness of fit, or the badness of fit in this case, because we're trying to minimize it. It determines the discrepancy observed. And here, we're going to be doing that many times. If you look up here, I don't know if you folks have used replications selected. Do you have that? So it's running it 5 times per set of parameter values. So it's running the model 5 realizations per iteration, per assumption for each parameter, for a given assumption about the parameter values, it's running it 5 times. And for each of them, it's evaluating that objective function. It's taking its mean over those 5, and it's using it then to judge whether this is the best iteration. If so, it takes the last of those outputs from main, and it puts into this DS infection best.
But you're still saving every run. You're saving root.infectious.ds there?
That's true, because we need to do this to run the objective function up here. In order to evaluate this objective function, that refers to DS infectious current. That's a data set in ourselves, because we can't refer to the mains data set, because that could be gone by now. Main is ephemeral. Main comes and goes. Main could have disappeared by now. So before main disappears, we salvage out the value from main of the data set, and we use it to fill our data set. And then shortly thereafter, we evaluate the objective function for that data set compared with the historic data set to find the discrepancy. And we do that then 5 times in turn. So this DS infectious current is going to be filled in 5 successive times for each of those successive those replications. And then if the mean value of them is the best so far, in that case, we're going to fill in this DS infection best from this value here. Yeah. 5 times. In this particular example model, they're running it 5 times. Yeah. So it's each of the values for the parameters is being evaluated 5. Now you can put in 500. I suspect they didn't do that because they wanted to run reasonably fast. Oh, 500 is the number of iterations. That's a different matter. 500 is the number of possible combinations of parameter values you're examining. So there's a hierarchy here of iterations, which are the number of different possible values for the parameter values. It'll be the equivalent of if I say I'm going to examine mu equals 1.0, beta equals 3.14159, and tau equals 2.71. That will be one iteration, and then I'd run it 5 times for that because of stochastics, because it's going to be variable from run of that to run of that. And for each of those, I'm going to be evaluating this objective function. And then so that's one iteration. A second iteration would be I have tau equal to 2.43, mu equal 0.781, and beta equal 1.22. That would be a second iteration, and I'm going to run now 5 different times, 5 different replications to deal with the stochastics involved. That would be a second iteration. Now, these iterations are going on in parallel in general, so that it could be evaluating replications of one iteration on one core and replications from another iteration on another core. But ultimately, it's the mean value between those that's used to judge whether this is the best iteration. Okay? So, question, Maria? Right. No, it's a genetic algorithm of some sort. It's the OptQuest engine. That's my understanding. Yeah. So it's they have OptQuest, and in fact, AnyLogic doesn't. I don't think it's really talked about a lot. But if you really explore this model a little bit, you'll find that there's some interesting things in it. For example, these values here. So to figure out sort of what's the current best one here, in sort of the current best iteration that's been reached, you'll notice that this is based on get best iteration, and that is I believe here, it's a call, so it's part of this experiment optimization recurrency iteration that does that. But there's certain OptQuest variable information that is used. It may be, here we are. So you'll notice here, get current param value. It's referring to this OQ var. That's an OptQuest variable that it's optimizing for contact rate. Okay, so behind the scenes, I believe it's accurate to say behind the scenes in this calibration, when you go and you say, I want to vary adaptive illness duration, basically it's going to allocate an OptQuest variable for you that then gets optimized, and you can interrogate through any logic, you can interrogate it to find out what's the value of that particular OptQuest variable to put it in to display it, etc. So you can ask it, get me the current parameter value for this certain identifier here, and you'll see that there's two of them right now as part of this OptQuest continuous variable. Is that helpful? Okay. Okay. So time is a ticking, and let me just see if there's additional features I want to say. So if you really want to understand what's going on here, you may want to, so I have some explanations of these. So first of all, it's worth running this thing so you can actually see it doing, undertaking this calibration. And some words of oh, okay, oh gosh, yeah, it's gonna cause problems because I deleted all those things. Now the two data sets are of different sizes. Okay, you folks can run it. Yeah, and basically what's going on is it's exploring the space, and it's trying successively more refined sort of values of the parameters. It's initially the best objective function is quite poor, then over time it gets better and better, and given current output, this current output shown in blue, so I recall it's the output from the current realization, and the best output shown in red is going to be from a particular replication from the iteration, the particular set of parameter values that seem best. Okay, so it's going to be running this thing again and again and again, and trying to identify the set of parameter values that over 5 replications seems to offer the best mean match as measured by this sort of mean squared metric, a square root of the sum of squares differences metric of match against the empirical data. Okay. Now, if you wanted to include a broadened function, this is what my exercise involves. Suppose you wanted to consider not just the current number of infectious people, but the number of incident cases. You could then add an additional term to the objective function that would involve another data set, and comparing another data set of data from the model against another data set of empirical data. And you could weight them. Exactly. And so it'll be trying to match them. You can also set it to try to automatically stop based on a statistical stopping criteria, which is based on taking the mean of the realization. So here, it tries to identify the minimum number of replications that will bring a certain confidence interval within a certain error percent of the mean. And and I think it's assuming, using some sort of central limit theorem type reasoning, law of large numbers. It's assuming that it's going to be normally distributed, and assuming a certain confidence limit will lie within a certain error percentage around the mean after a certain number of replications. So it's going to try to get this kind of error bar down until it lies within the certain percentage around the mean value. So after 40 replications, for example, it may go from a very large error bar with fewer replications, successively smaller until the point where it fits within there. Okay. Yeah. So thank you. And I'm trying to remember if I have a specification of that, but if I don't, then then I stand remiss, and I'll explain it to you right now. So there's two basic mechanisms for specifying constraints of sorts. One has to do with constraints on the parameter values. So, okay, there's actually, I should really explain it as three. So if you go to this calibration experiment, you'll find here's a specification of how to vary the parameters and over what sort of range to vary them. I think this step is only active for a discrete case, not for a continuous case. In any case, here you can specify the range in which to wish to vary parameter values, fair enough. But there's further a set of constraints and requirements that you can specify. Basically these involve, you can specify a constraint like, parameter A plus B plus C must total to less than 1, right? Or what have you. And those can be specified in this constraints area. And then, and so here, before we run the simulation, we test, is this a valid set of parameter values? And if so, then we run it. If not, we don't run it. But then there's this requirements, which after a simulation is run, you check the basic face validity of that result. For example, if it's a stock and flow model, are there negative stocks for some physical a physical quantity which can't go negative? That would indicate a numerical analysis type problem, problem in the sort of numerical solution, and we throw that away. So you can specify constraints at that level too. Are those helpful comments? Okay. Any other questions about this? Yes.
You said there was like an exercise that was good.
Yep.
Is that on one of the websites?
Yep.
Okay.
Yep. It should be part of the materials that I've given. I think it's part of the challenges materials. There's one file of challenges. Priyasri, maybe you could look into that. Oh, is your computer functional again?
No, but I can
look at what that machine. It's on the Google Drive. I think it's in the challenges. It's a optimization challenge, I think. Yeah, that's a little exercise my students have done and seems to recommend itself. Okay. Any other questions? That it works with this example. Any other questions? Okay. Again, I wish I could spend more time on each of these topics.